All right, we're live. And let's see. Yes, we are live. Welcome back to another episode of Composites Weekly. Today's episode, I've got David Leach joining me. He is the business, business. He is the director of business development at ATC Manufacturing. He is a technology leader in the field of thermoplastic composite materials. And he's going to be speaking next week at ECCM, Europe's leading conference on composite materials. The topic of his discussion will be the transition from Thermoset to thermoplastic composites. So I invited David to join me. This event starts next week. I believe early next week, Tuesday of next week. So he'll be flying out to France. And David, I want to just say thanks for joining me kind of on short notice. We had some back and forth discussions on LinkedIn, and you were more than gracious to spend some time with me today. So I appreciate your time.
All right. Thanks. Appreciate the opportunity to share this with your audience.
Yeah. So tell us a little bit about what you do currently. I know you're with ATC, and just to give our listeners a little background, they're pioneers of the adoption of continuous fiber thermoplastic composites in aerostructures. And they supply, I didn't realize this, they supply more than 800,000 parts per year, operating in a state-of-the-art facility up in Eastern Washington. You work with them to some degree. I don't know if you're still in the role as director, the director of business development, but you can maybe share a little bit about your background and your role there at ATC.
Sure. Maybe just to start a little on my background. I've been involved with thermoplastic composites for most of my career, which is about 40 years now. Actually, I originally joined a large British chemical company, which had a very big polymers division, did a wide range of polymers, everything from kind of polyethylene and polypropylene up to high performance polymers. In fact, they were the original inventors, developers of the PEEK polymer. And in fact, the Victrex company was actually spun out of them. Around the same time that I joined, they were starting a new initiative in higher performance composites. Kind of short fiber molding materials were already available, but they saw an opportunity in developing long and continuous fiber materials. So I was involved from the beginning with development of PEEK continuous carbon materials. They were called APC, or aromatic polymer composites.
Yeah.
In fact, that business went through a number of hands and is actually part of Science Co now. So
sure.
They still manufacture those materials using the same processes. I was with them for many years developing materials, doing qualifications, working in customer support and initial thermoplastic composite kind of usage, mainly in aerospace and some other kind of high performance applications. Thermoplastics has sort of gone up and down over the years. So I, at various times, I've also been involved with thermosets on interiors with like phenolic materials, epoxy structure and secondary structure. And then I was working for a while with Henkel on the development of benzoxazine thermoset composites for high temperature and long out time applications. But I joined ATC in 2016, and just to focus on ATC a bit more, we were founded by a former Boeing engineer, Dan Jorgensen, who left Boeing in 2004. He'd been involved in some of the early developments of thermoplastic composite forming and applications within Boeing. He decided it was a really interesting area of technology, had a lot of potential, so he decided to go off on his own and set up ATC. That work had been done at what was then the Boeing Spokane, later became Triumph facility. And so that's why our facility is up in that area, starting initially in Eastern Washington and then actually moving over to North Idaho, just over the state line into Idaho.
Okay.
So we're a large-scale fabricator. As you mentioned, we have supplied quite large quantities of parts. In fact, even more than you mentioned, about 1.1 million.
Wow. Okay.
1 year. And it's all continuous fiber reinforced materials with carbon and glass some fabric, but a lot of unidirectional tape materials with PEEK, PEC, PEI, and so on polymers, so high performance polymers. We take in the raw materials, in some cases laminates, organosheets as they're often known, or prepregs if they're unidirectional tape. We make our own laminates using continuous compression molding process, which is a very efficient method of making laminates. We also make profiles, things like C channels and so on, directly using the CCM process, and other profiles like omegas. But the majority of our parts are stamp formed. So we take the laminates and then heat them rapidly, normally infrared oven, and transfer that over to a quickly closing set of dies that form the hot blank into the finished part. So we have 10 stamp forming presses altogether, ranging up to 60 inches by 30 inches. So we can make some quite good sized parts. And we've certainly seen there's been quite an upturn in about the last 8 or 9 years in the use of thermoplastic composites.
Yeah, most of these parts are for aerostructures, right? I mean, all of these you're supplying to the aerospace application.
Yes, because Dan, our founder, came out of aerospace. We've always been focused on aerospace and defense. Yeah, not a secret. The majority of it is commercial aircraft oriented. Boeing, again, as Dan had worked at Boeing, we've always had close association with Boeing applications.
You know, I caught your one of your posts on LinkedIn where you're talking about you'll be speaking next week or giving a presentation at the European Conference of Composite Materials, ECCM. Tell us a little bit about that before we get into your topic, because I thought obviously the topic's super interesting to me. Again, the title is The Transition from Thermosets into Thermoplastics. And we're talking, as the technology continues to, evolve and it opens up more than just the aerospace industry. There's applications outside of that, which is pretty exciting. And we'll talk about that and some of the reasons for those advantages over traditional thermosets. But I wanted you to, if you would, talk a little bit about, is this your first? I'm sure you've attended this conference plenty of times in the past. I've actually never been. Tell us a little bit about this conference over in, is it outside of Paris? It's what is it, Nantes?
Yeah, this year it is in Nantes, in the western part of France. Of course, that area is well known for composites activity. There's a large Airbus Thermoset composite fabrication center there. Also, Daher has a big facility where they do thermosets and thermoplastics. And there's also a quite significant kind of R&D activity there as well in that area. So it is quite a concentration of composites.
Sure.
ECCM kind of rotates around European locations. It typically alternates with the International Conference of Composite Materials. So they're usually sort of every other year alternating. And I know there are over 1,000 people registered for it. So it's quite a large conference, and there's a small exhibition with it as well. I have been, although not for quite a few years. It does tend to be quite technically oriented. Certainly quite a number of people from industry, but also quite a lot from academy and government labs and so on as well.
Sure.
So it's probably a bit more sort of fundamental science oriented than some others, like say the SAPI conference or things like that.
Right. Were you at SAMPI a few weeks ago?
Yes, I was down at SAMPI in Long Beach, in fact, as well. I was actually chairing a session and running a panel down there on.
Fantastic! Well, sorry that we didn't get a chance to meet in person there. I was there for a couple of days as well. So, well, great. Well, tell us, if you would mention about your, obviously your presentation, the move from, or the transition from thermosets to thermoplastics. I mean, you give some great points in your presentation on how, even outside of the aerospace industry, there's new opportunities for these materials as they continue to advance. Most of us are very familiar with, as you mentioned earlier, you got PEEK and PEC, and from a toughness, or I guess one of the major benefits of TPCs is, flammability, resistance, high resistance to aggressive fluids. So if you would maybe talk about kind of the foundation for your topic and why at this time are you presenting on this?
Yeah, sure. It was sort of invited by one of the session chairs. So it's not what I'd call a hard technical presentation. It's more of an overview of where have we got to with thermoplastics and where are we going.
Yeah,
because it's sort of an interesting situation, almost a bit of a case study. The composite materials, as we mentioned, have been around for almost 40 years now. With, as an example, the company I was involved with, developing PEEK carbon originally.
Right.
And then Tencardi, now Toray, developing some of the fabric laminates with things like polyethyramide and PPS with carbon and glass fabric. And I think back then in sort of the late 80s, early 90s, everybody really thought that thermoplastic composites were going to sort of take over the world. And well, they didn't. Thermosets have still ruled the day for a very long time. But interestingly, although the thermoplastics have been around for a while, the reasons for using them are sort of more compelling than ever, and there's tremendous interest in much more widespread use on sort of next generation of various types of aircraft, but also things outside of aerospace, as you mentioned. If we go back to the early days, people really latched onto the toughness, which you mentioned. Back then, the thermosets, typically epoxy materials, were quite limited in toughness, and if you did toughen them, then you really compromised a lot of the high temperature use, hot wet performance, and so on. And so you could either have an epoxy that was tough or one that was high temperature, but not both. And so thermoplastics were sort of latched onto very quickly, applied on things like the F-22 fighter from Lockheed Martin, areas like the area forward of the cockpit, so a lot of the nose internal structure, and particularly the weapons bay doors. Those open up on the bottom side of the fuselage and open up in flight, so they can have quite significant aerodynamic loads. But of course, also a lot of damage, things that might be thrown up from debris on runways and so on. And so there's a big driver of having a very tough material there. Similarly, and actually over in France, Dassault used some of those materials on the Rafale fighter, which was being developed around the same time in the central fuselage area. Is more internal, so not as much toughness driven, but particularly high temperature driven with, as I say, then the compromises that you had to make in terms of kind of hot wet performance with epoxies. So the first wave was very much performance. And while people had ideas of rapid forming, the technologies that were available then were just derived from thermosets. So there was a lot of hand layup and high temperature autoclave, which did yield good parts, but were very expensive. Now, there were some techniques that were developed, like superplastic diaphragm forming, which did enable you to make quite complex parts. But again, sort of very expensive materials being involved with them. The thermoplastics, while they met the performance criteria, did not really meet the economic criteria. And so, the adoption of a lot of unidirectional tape materials sort of went on the back burner. On the other hand, there were applications in things like the interiors and cargo hold, which tended to be high volume. I mean, one example we talk about is smoke detector pans. Smoke detectors are required within the cargo hold of commercial aircraft in case there's a fire or even a smoldering situation starts down there. And so there's actually a lot of smoke detectors all over the lower part of the fuselage in that cargo hold area. And the pans originally were going to be sort of hand laid up out of thermoset and cured. And it was realized that was going to be a very kind of expensive process, whereas rapid forming of glass fiber reinforced thermoplastic, glass fabric reinforced thermoplastic could yield these pans with very fast cycle times, and so give very good economics. So that was one of the sort of first higher volume applications that was developed, and some of that went on in Europe with some similar applications. But again, the founder of ATC, Dan Jorgensen, was very much involved in that with Boeing. Then really the emphasis switched to Europe, and in particular, I've got to recognize a lot of the work that's been done at Fokker, or GKN Fokker, particularly led by Arne Offringer, who's the director of the Thermoplastics Technical Center in Hogeveen in the Netherlands. So they really went out to develop a lot of welding technology. So some of the next applications were things like the Airbus A340 and A380 leading edges, which started to really realize not just the benefits of rapid forming and some of the ribs that went into there, but also the welding those ribs to a skin. Initially resistance welding, later induction welding was developed. And unfortunately, while neither the A340 or A380 have had very long production cycles, it did really demonstrate the cost effectiveness of thermoplastic, and particularly prove that welded technology was indeed viable in flight and in a fairly damage prone area, right on that leading edge of the wing, where you know, you can receive damage on the ground. You can also have hail or even bird strike at times. So it did also utilize some of the toughness benefits still of thermoplastics. So that was kind of a pretty significant step forward. Then probably the next one, again, we have to say that you know, both the 787 and the A350 sort of came along in the early mid 2000s there. That was a big opportunity for higher volume applications. Of course, with a lot of composite structure in general, there was a desire to use composite substructure. You don't want to put aluminum next to composite structure if you can help it, because of potential galvanic corrosion. So there's a lot of opportunity with more structural parts, things like stiffeners in particular, you know, various joining pieces, basically joining larger sections of fuselage together. One of the ones that certainly got a lot of attention in A350 has been widely publicized, the frame clips that join the fuselage skin to the fuselage frame. So there's a large number of those, well over 1,000 per aircraft, that are stamp formed by various suppliers in PPS or PEEK carbon fabric materials. Certainly on the Boeing side, there was a lot of use of unidirectional tape, particularly with PEC, into much more structural applications and indeed in primary structures. So that has sort of brought us up to where things are today in terms of applications. But going forward, there's a tremendous amount of interest. I mean, first of all, if we just look at commercial aircraft, we've seen in Europe a series of programs, one called TAPAS, and then through Clean Sky, and the development of the multifunctional fuselage demonstrator program, which has involved a lot of European companies and other organizations like DLR in Germany and NLR in the Netherlands, to really prove out the technologies and to incorporate a lot of design ideas about how you can integrate structure, how you can integrate systems with the structure, how you can use welded assembly and different types of welding, from resistance to ultrasonic to induction and so on. And of course, the multifunctional fuselage demonstrator, or MFFD, has been shown, demonstrated a few places. I think it's going through final joining process of the upper and lower sections in the very near future. And then in the US, we have the NASA High Rate Composites Manufacturing Program. So that is looking at the ability to make commercial aircraft at high rates, up to 80 per month for a next generation single aisle. So it is evaluating thermoset prepreg, resin infusion, and there's also a significant, very large stream to do with thermoplastics, which ATC is a member of. And in particular in thermoplastics, we're looking at large-scale stamp forming to expand that footprint of parts that can be manufactured up to much larger sizes. Also, higher rate continuous compression molding. You might imagine parts like floor beams are an ideal candidate there.
Sure.
But then also, again, how you put it together. So really advancing welding technology further.
Yeah.
Certainly the examples that are flying around have all been very successful, but I think we'd have to say they've been sort of point solutions, and really need more generalized solutions as to welding, particularly of unidirectional tape parts, which obviously you want for structural assembly. Induction welding, as an example, is a little easier with fabrics, because the nature of the fabric, with carbon fiber fabric, you tend to induce eddy currents around the weave sort of loops. With UD tapes, it's a little more challenging, and you really don't want to use susceptors there. As I mentioned, there's also other welding techniques, and I think there's still a lot of learning to do as to what's the best welding technique for different types of application. You know, if you're joining two pieces of structure together versus more a long stiffener to a skin, for instance, that type of thing. And then also the downstream processes, as we found within our company, non-destructive inspection is a little different with thermoplastics. The attenuation of the thermoplastic is different to that of thermosets. And so you have to do some different things around developing what is the acceptance criteria and developing standards for inspection. And then finishing, surface preparation and finishing, again, with a lot of the materials, polymers that are being looked at being semi-crystalline. Those by their nature are quite inert, have very low surface energy. So you need to look at different types of surface preparation techniques that are going to activate the surface adequately, and also going to be robust in a production application. As we all know, it's one thing to do something in a lab or even a pilot scale. It's a whole different thing to roll it out into a full kind of a manufacturing plan and ensure that you're going to meet the required criteria, you know, day in, day out. So anyhow, exciting time. That's commercial aircraft. Now, in addition to that, we have advanced air mobility. As we know, that is advancing rapidly. We see a lot of work with companies like Joby, Archer, Lilium, advancing through certification processes. While the initial quantities of advanced air mobility vehicles will be relatively low, we know that for them to be viable, we're going to have to be building thousands a year. And all the companies involved in AAM are definitely looking at thermoplastics as a solution to meet rate, because of the fast cycle times that can be achieved with forming, and, you know, forming a part in a matter of a few minutes rather than hours. So that's advanced air mobility. Unmanned vehicles, obviously there's huge interest in, you know, all types and shapes and sizes of drones, from everything that might be sort of package or you know, commercial delivery type vehicles, right through to kind of emergency services, through to the defense side. So everybody is looking at making large quantities of drones. And again, both drones and advanced air mobility really fit very nicely for thermoplastics in terms of the sizes of parts that we can manufacture now, where there's already existing technology.
I'm just curious on the approval, the validation testing that all happens, and all the way to the point where it, you know, parts get approved for commercialization. What kind of time frame do you look at in this industry? I mean, what does that look like from start to finish?
Yeah, that's a good point, and this is a bit of the lessons learned in the almost case study situation. Of course, it's pretty hard to convert something over that's already in production, whether it's like a metallic part or a thermoset part, to a completely different material and technology. Generally, unless there's some sort of problem with that to start with, that says, okay, you've got a big driver that you got something you got to change or fix, because the time and cost of those approval processes are very long. So this is where the best opportunity is generally on new designs, kind of new aircraft or new vehicles of whatever type. But even there, I would say with even if you have things like material specifications, process specifications, design allowables, which whether it's aircraft or something else, these are going to be used in generally quite highly loaded applications. So you need some sort of design basis to start with. So even if you have those, I would say it can easily take 2 to 3 years just to get a part all the way through the full approval process. That involves several steps of what's called pre-production validation or PPV, then into first part qualification, first articles, and of course all of that has to have oversight from whoever the regulatory authority is. Usually if it's aircraft in the US, it's the FAA, but also the original equipment manufacturer being very involved as well, as they normally own the design and the criteria and so on. Certainly that has been one of the obstacles to getting thermoplastics into wider range of applications. But from a material and process spec point of view, one of the interesting things is there's now becoming much more of the publicly available standardized databases, such as the NCAMP system, that's run through Wichita State from NIAR, the National Institute of Aviation Research, where there are these standardized specifications that companies can put their materials through, or standard test methods, I should say. And then that data is published by NIAR and then can be used by anyone in the industry. And then again, there are sort of parallel process specifications that go along with that. And so fabricators can get their processes approved to those fabrication specs as well. And up until a few years ago, there were virtually no thermoplastic materials in those databases. But now there's probably at least half a dozen and a lot more on their way.
Sure.
You can go onto the NCAMP website and see what's qualified and also what's in process from multiple material manufacturers in different forms, carbon fiber UD tapes, carbon fiber fabrics, and so on as well.
Do you spend much time in the additive manufacturing side of things and how that's playing out in thermoplastics right now?
Well, yeah, that is quite an interesting area. There's a lot going on, and obviously traditional sort of additive, which started with unreinforced or short fiber reinforced, is starting to overlap quite a lot with long or continuous fiber materials, as people are now doing additive with that as well. We don't actually manufacture parts using additive composites ourselves, although we do use additive internally to make kind of show and tell type demonstrators to get an idea of what a part's going to look like, and also a lot of internal fixtures. So we're sort of involved in the area, and also working with some of the people, just to mention one like Electro-Impact, which has their SCRAM system, which can do both combinations of additive and traditional fiber placement all in the one unit. So working with them partly through the HiCamp program and other activities as well. So I think it's a good point that there's starting to be much more of a convergence of these types of processes to achieve what's kind of the best solution for a finished part, and potentially combinations. So as an example, you might stamp form a part and then additively manufacture additional kind of build-ups or fastening points or whatever onto a part.
Yeah. It's incredible. Well, David, I know we're running short on time. I do want to mention for anyone that plans to attend the ECCM, it's the 21st, I guess that's the 21st annual conference that's taking place next week. How can, we'll post the website, but what day will you be speaking at the event?
Yeah, my presentation is on the 2nd of July, the Tuesday, which is actually the first day, and it is at 12:30 in the afternoon.
Okay.
Yeah, it's going to be quite a busy conference. There's quite a number of parallel sessions, so
I'm sure.
I'm looking forward to it. Yeah.
Well, we'll certainly be posting a link. If people, I'm sure you don't mind me putting the link to your your website, how people can learn more about what you're doing at ATC, and then obviously we'll have a link to the program as well, and try to find where your presentation will be, and then post the time for our listeners if they're going to be any of our listeners that happen to be in France next week attending that event. I think sounds like a great venue, very technical venue, but obviously a lot to take in 2 or 3 days, right?
Yeah, it's going to be a very busy conference. Yeah. Sure.
Yeah. David, thanks so much. I really appreciate your time today. I hope we can maybe catch up in person at CAMX in September if you're going to be back out in I guess you're already in California, so maybe that's
yeah, sure. I plan to be at CAMX, so yeah, I'd love to see you, and anyone else who's listening as well can reach out to me.
Yeah, that'd be great. Love to see you in San Diego. That would be fantastic. So, and again, you all can find more about. We'll be posting a link on our show page for anyone that is interested in learning more about the topic David will be speaking on, the transition from thermosets to thermoplastics. And it should be a great event. David, thanks again, and hope you have have a safe flight out there. Have a great trip next week, and enjoy your time.
All right, great. Thanks very much.
Absolutely.